so here goes. All right, so problem 45. Suppose Ford currently sells 250,000 Mustangs annually. The unit cost, including the delivery cost to a dealer, is 16,000, and the price is 20,000. And the current elasticity of demand for the Mustang is minus 1.5. Now, right away, we're defining a new term, elasticity of demand. And if you remember back from economics, what the elasticity of demand is showing is the change in demand for the change in price. All right. In this case, we are going to go ahead and plug in the data here. So the current demand is 250,000. Current price is 20,000. And cost is 16,000. And elasticity is minus 1.5. So these are all values that were given in the problem statement. Now, let's go ahead and make some range names as well. Okay, so let's look at what we mean when we say the demand function with constant elasticity. What we're saying there is that demand is equal to a constant times price raised to the value of elasticity, okay? In other words, if you want to think of it in these terms, this elasticity is the exponent of price, all right? Elasticity is the exponent of price. So what does this mean? Well, this means that demand, in this case, if that's a negative exponent, is what? It's inversely proportional to price, okay? And more to the point, it's inversely proportional to price raised to the 1.5 power, okay? In other words, it's going to be a nonlinear function, right? Now, one of the things we have to do is we have to calculate the coefficient, this A coefficient, all right? That A coefficient is not given to us. But one of the things we do know is what? Well, we're given a single point where we've got demand and price and elasticity. So we've got three values. We can calculate it, right? Yes. Um, the constant. This is not a linear problem, so it's not an intercept. It's more of a magnitude. It adjusts the magnitude up and down. Right? So we can calculate this constant just by taking this demand equals A times price raised to the elasticity and rearranging the terms, right? And what we end up with is A is equal to demand divided by price raised to the elasticity. So let's do that calculation. A is equal to demand divided by price raised to the current elasticity. And when we do that, we get this really humongous number. And I got to be honest with you, the first time I saw this number, I said, that can't possibly be right. But then I looked at it and I said, well, no, wait a minute, because I've got, 250,000 demand, I got 20,000 price. Maybe it is right. So let's see. All right. So now let's plug in this model. All right, so it says we want to determine a profit maximizing price for a Mustang. Do this when the demand is a function of the constant elasticity type. All right, So we want a new price. This new price is going to be a decision, excuse me, yeah, it's going to be a decision variable for us. Okay? So let me go ahead and make some more names here. Okay, so I'm not going to be real particular here. I'm just going to plug in 16,000 because that's the cost. All right. So I know if I'm trying to maximize profit, if I sell it at cost, my profit's going to be what? 0. That's what I'm going to expect to see. All right. So let's see if that happens. So my new demand is going to be equal to what? Well, demand is going to be equal to this constant A times my price raised to my elasticity. All right. So right up here, you can see I've got that formula, which is exactly the same as this formula right here. Okay. So there's my demand. And I'm just going to get rid of the decimal places. And so then my profit is going to be equal to what? Well, it's demand times price minus cost, right? So it's going to be demand times price minus cost. And profit is going to be my objective function for this model. Okay. All right. So there's my model. Now, again, I could solve this mathematically, but it's so much easier to use Solver. So let's do that, okay? So let's go in to Solver. And I want to use profit as my objective. I want to maximize profit, so far so good. I want to do that by changing price. Now, do I have any constraints? Well, let's think about this for a second. Clearly, I don't want my decision variable, which is price, to be negative. Well, that's not going to happen, right? Because I've got the make unconstrained variables not negative, right? So that's not the worry about that. Are there any other constraints that I can think of for this problem? Demand has to be greater than 0. Okay. But if price is greater than 0, doesn't that force demand to be greater than 0? I think it does. So should I make price greater than cost? Perhaps. I can put that in. I don't think it's necessary, to be honest with you, but let's go ahead and put it in just to be on the safe side. All right, so add. Whoops, what happened there? All right, price has to be greater than or equal to cost. All right. Can I think of anything else? I can't. All right, I can't. So select a solving method. Well, we know this is a nonlinear problem, so GRG looks like the way to go. Now, I'm going to go ahead and click on options first because I want to show you for GRG nonlinear, I want to use the multi-start function, okay? And multi-start works best when you put bounds on the variables, all right? What does that mean? Well, that means that the decision variable is price. I put a minimum on price. I said price had to be greater than or equal to cost. So if I'm using the multi-start option, I've got one bound, but I have to add a second bound if I really want this to work right. because what multi-start's going to do is it's going to choose random values, 100 random values between the bounds that I place on the decision variable. So let me go back to my problem and add a new constraint for price. And that constraint is the price has to be less than. Now, what value should I choose for less than? I don't know. I don't know. I probably want it to be more than the current price, but how much more? It's a guessing game. I'm going to speculate for no good reason other than just to try it out that I'm going to use 2 times the current price, so 40,000. Okay. Now I've hard coded that 40,000 into solver. That's not good modeling practice. Good modeling practice, I would have a value on the spreadsheet that said maximum price, and I would use that. But for now, I'm going to go with it, okay? So I'm just going to say I want to choose 100 random values between 16,000 and 40,000 and find the price that maximizes profit within that range. Yes? No, not really. I mean, I said it's 250,000, but what if that's in units of thousands, right? Not. Clearly, you don't sell 250 million cars in a year, but suppose it was, all right? So it doesn't matter to me whether it's integer or not, okay? All right, so let's solve and see what happens. Wow, converged on a solution already, and the solution was 40,000. All right, so now we get to find out whether this is the right answer, okay? Let's go back into solver, and let's change um, the maximum constraint. Let's change it to 50,000. Try it again. Solver converged in probability to a global solution. And now, what is the answer? 48,000. Okay. So it found a local optimum at 40,000 the first time. This time it found a global optimum at 48,000. Okay. Now, I suspect for a lot of people this is a little bit unsettling. That you built the model, you ran it, gave you an answer of one value, and you didn't accept it. And so you ran it again to see if the answer changed, right? What do they say the definition of insanity is? Expecting a different result, right? But in this case, we did get a different result. So what does that tell you? Did I set my bounds too low? Possibly. But that's the point. This is what I want you to understand about nonlinear optimizers. You gotta sort of work with them. You gotta play around with them a little bit. You can't just take the first answer you get as the right answer. Let's go back and see what solver told me when I used the 40,000 as the maximum price. Okay, it still thinks it's converged to a global solution. But we know that's not the correct answer. What happens if we change this Instead of 50,000, what if we made it 100,000? Now, would any of you pay 100,000 for a Mustang? Maybe if it was a Shelby 65 GT, but solver converged in probability to a global solution, and this time it came back to 48,000. All right, so I've got a pretty good feeling now about 48,000. I had a good feeling when it was at 50,000 for the upper limit, and now I have a really good feeling because I've given it a wide boundary, and it still converges on 48,000. So I'm going to say 48,000 is the answer. And by the way, the solved workbook will become available on Blackboard at 8:30 tonight. So you can go back and look at the answers beginning at 8:30 to see if we were correct. All right. What questions do you have? Yes. All right. So let's go back and explore that. All right. So you're saying if I choose not to use the multi-start option, okay, so I don't use multi-start. And so I can say I can delete that constraint, and the only constraint now I have is unit cost. And you're saying if I do that, well, let me do one other thing. Let me go back and put this at 16,000 because that was my starting point. Okay. So now I'm not using multi-start. I'm at 16,000, and I've only got the one constraint. So now I click on solve, and in this case, you're right. I got to 48,000. So would I have gotten there without multi-start? Clearly, the answer is yes. The problem is I did not know that going into this. All right. And if I had just done it without the multi-start option, I might have got 40,000. I don't know. I mean, I didn't this time. But there's a problem where I might have got 40,000 because 40,000 was an optimum at some point. So the question is, should you always use multi-start? And my answer is yes. Best practice would be to use multi-start. And if you use multi-start, then you have to, well, you don't have to give bounds, but it's best to give bounds. Otherwise, the problem just wanders around aimlessly until it solves. That's a good question. Should you use multi-start all the time? Yes. Should you use bounds all the time? Yes. What should those bounds be? I don't know. Making them wider probably works in your favor, though. Other questions? Yes. No. Yes. Well, but you're constraining the decision variable. Okay. Look at look at this problem again. There's no constraint other than the constraint on the decision variable, which is price. There's no resource utilization. We're not saying how much steel do we have to make Mustangs. We're not saying how much freight can we ship Mustangs with. None of the other parts of the problem are involved here. The only thing we're looking at is price and how price affects demand. No, yeah. I could say use multi-start and don't require bounds on the variables, and that'll still solve. Um, but as I suggested to you, sometimes it'll get stuck, and it will just keep going through iterations, and it won't converge on a solution if you don't put bounds on the variables. Yes. They're randomly chosen. Yeah. Because the problem with evenly spaced is that would assume that the uh, global optimum is between evenly spaced values, and you can't make that assumption, so it does randomly select it. Well, no, because it's randomly selecting a starting point. Remember, when it, from a starting point, it's going to go in both directions seeking the value. All right. If it goes in one direction and it's a negative slope, it knows I don't have to go that any further in that direction. So then it backs up and goes in a positive direction until it finds a maximum. In this case, because it's a maximizing problem. If this were a cost minimizing problem, it would be the other way around. Yes. If I use multi-start, I'm trusting it to find the global optimum. Yes. 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 Yeah, that's one of those interesting problems that people deal with, and the answer is that's why you do multi-start. Okay, if you can have multiple local optimums, particularly if a large problem with multiple decision variables. You can think of in terms of you can find an optimum all over the solution space. All right, but somewhere you hope is a global optimum, and that's where the multi-start is trying to find. All right, it's possible that that global optimum you can't ever get to. You might get stuck in a valley somewhere and never find your way out. And that's one of the problems with the algorithm. That's why it says, again, look at what the solution says when it when it reaches an answer. It says, no, it says not that it converged. It says in probability to a global solution. It does not guarantee that it's the global solution. It probably is. For our models, it most certainly is. Almost certainly is. But as models get more complex, that guarantee goes out the window. Okay? All right. Well, that's with elasticity. Now let's look at linear demand. And this is where the constant A would be the y-intercept for the problem. Well, hang on a second. Let me